Okay, hello from me. This is Konstantinos, University of Southampton. So I'd like to welcome you to the morning oral presentation. So we have, the topic is on learning for control. We have 4 papers, 15 minutes each, and we'll try to keep 13 minutes for the presentation and 2 minutes for questions. So the first presentation is by Heng, who is at Harvard. The floor is yours. I'll give you a note.
Okay.
I'll give you a note when we're about 12 minutes.
Okay.
Perhaps, so you can.
Okay. Yeah, so my name is Heng. So today I'll present uncertainty quantification of set membership estimation for some control and perception problems. And especially we want to revisit this notion of a minimum enclosing ellipsoid from the computational perspective. And before I get started, so I should give all the credits to this amazing undergrad student, Yukai Tang, who did the visiting student in my group last year. And then I think he's joining Princeton as a PhD student, so we weren't able to fund him to come here, but I think we will see him somewhere else later. So let me give you a little bit motivation of why we care about this problem. So we focus on this setup where we are interested in estimating some model from some measurements, right? So here I denote the model as the theta lives in some set, and then we have collected a bunch of measurements z from zi equal to I equal to from 1 to n. And then in order to estimate this model theta from z, we're going to place some assumptions, right? So we're going to say this model is correlated with this measurement z in a way that this residual function of theta and zi should be equal to 0 if this zi is a perfect measurement. And then in practice, you get noise in your measurements. So I'm going to say this equation is not going to be satisfied perfectly. So I'm going to say this equation will be equal to some noise vector epsilon I. And then I'm going to place some distributional assumption on this epsilon I. For example, the most common one is Gaussian, right? So that's what we do in practice. And then we can solve this maximum likelihood estimation problem where we try to minimize the sum of squares of this residual vector. And then I can place a robust cost function to make sure my optimization problem is not sensitive to the existence of outliers. So I did my whole PhD in solving this kind of problems. But then later on, I started questioning, is this really the right way to go, at least in some cases? So there are 2 questions I think that are worth asking for this framework. So the first question is this Gaussian or any type of distributional assumption really true when we have measurements from in the real world, especially when the measurements are obtained from neural networks? And the second question is, how about getting an uncertainty estimation from these optimization problems? Because when you solve this optimization problem, usually you get a single estimator. So for the second question, in practice, what people do is that when you solve the optimization problem, you form the Fisher information matrix at the optimal solution, and then this is usually called the Kramer-Rao lower bound. But then this is known to be an underestimation of the true uncertainty. And then to answer the first question, is this Gaussian assumption really true? So we did this thing that I believe nobody has ever done in the community, which is if I really plot the noise vectors from some neural networks, and I'm going to check, are these noise vectors really Gaussian or satisfy some distributional assumptions? So here is the question that I care about, and this is a textbook computer vision example. You will see in many computer vision textbooks. So the forward problem here is you have a car, right, in a 3D CAD model, and then this CAD model gets rotated and translated to your camera view and then gets projected onto your 2D image, right? So that's a forward process. And then the inverse problem here is I take an image of this car and I want to estimate the 3D rotation and translation of this car from this single image. So what you do in practice, you use some neural networks to detect some key points of this car. For example, the mirrors, the wheels and things and so on. And then you formulate this model estimation problem where my model is my true rotation and translation RNT, which lives in some Riemannian manifold SO3 and R3. And then my measurements are these pairs of 3D and 2D key points, right? So, and then my assumption is that the 2D key point should be a perfect projection of these 3D key points after I do some rotation and translation. And in practice, you're going to get some noise from these neural network detections. And then what we did was, if I have some ground truth rotation and translation, then I can really compute these, noise vectors, right? That's very easy. And then I'm going to do some multivariate normality test, to see if these vectors are really Gaussian. And if you do this, it's very surprising, or maybe not very surprising, that these vectors look nothing like a Gaussian vector. And in practice, we tried very, very hard to see, if I massage this problem a little bit, I just took a subset of these noise vectors and see if they are Gaussian. Then, we tried very hard and none of these works. And you can look at these, there are multiple multivariate normality tests that you can do here. So here, I think we did about 6 by 6 multivariate normality test here, and it only succeeds in once, and fails all the other 35 normality tests, right? So the message here is the noise vectors generated by neural networks may be very difficult to fully characterize in distributional sense. And then we looked into what are alternative ways that we can do model estimation. And then we came to this very old work in control theory, which is called set membership estimation. So the setup is the same, but then the only thing differs is the assumption. So I'm going to assume that I don't know the distribution of these noise vectors, but I only know that they're unknown but bounded, right? So I'm going to assume that I have some noise bound on the two norm of these noise vectors. So I call beta I here. And then I'm going to formulate this set S, which is a subset of all the model parameters that are compatible with this assumption, right? So basically, you use the fact that epsilon I is equal to this residual function, and you place the two norm constraint on the residual function instead, right? You get a set that is defined by constraints on the parameters theta. So and then we revisit the two questions that I asked before, right? So is this assumption now a better assumption? Well then, some people may argue that this is not a good assumption either, but then at least in certain cases, we can show that you can use some data-driven methods to really rigorously characterize these noise bounds beta I, right? So in a sense that these noise bounds are not just came out of my head, but they're really calibrated using some data sets, which I think conformal prediction is not a unknown topic for this conference. I think you can see other works there too. And then what about the other question? How about uncertainty? Well, then this is an easy answer because this uncertainty comes for free, right? Because I formulated a set, so I can really characterize how large this set is. But this set membership estimation is really, so I'm going to give you two examples of this set membership estimation. The first one is the computer vision example that I told you before, but now instead of doing a maximum likelihood estimation, I'm going to formulate this set, which is a subset of SE3 defined by these constraints by these 2D and 3D key points. And then the other question, which is an iconic example in control community, which is system ID, right? So I have this nonlinear dynamical system, which is linear in my parameters, theta, and then I collected a trajectory, and my goal is to estimate the theta from this trajectory. And I can formulate the same problem by assuming that the noise of the dynamics is unknown but bounded. And then I get a set, which is defined by actually quadratic constraints, and you can easily see that this is actually a convex set. Okay, so I've done set membership estimation for two examples, and you can see that set membership is really, really wonderful, but then except that I've literally done nothing, right? So the only thing I've done is I placed some assumption on the noise vectors, and then I wrote down this set, but then I didn't tell you, for example, how can I even sample from this set? Is this set even empty or whatsoever? So, and then if you really have the power to plot these sets looks, really, really wild. On the left-hand side, I have these uncertainty sets of the 3D 6D poses. So they are decoupled in the rotation and translation space. And on the right-hand side is a convex set. It's a convex set defined by quadratic constraints. But then you see that you have many sort of edges and faces of this set. And then what I'm going to do now is I'm going to try to simplify this set, right? So for example, my goal here is, if I can find a very simple representation of this set, I can, for example, find the minimum enclosing ellipsoid that encloses these sets. Then what I can do is, for example, two things. The first thing, I can take the center of this ellipsoid and I treat it as my best point estimate. And then I can use the semi-axis of this ellipsoid to use as error bounds, right? For example, if you want to do robust control, you may probably consider that. And then the second thing I can do is once I get these ellipsoids, I can do simple rejection sampling, right? So I can just sample uniformly inside the ellipsoid, and then I take the samples once they satisfy these constraints. And if your ellipsoid is very tight, then I can have a very high success rate in doing the sampling. So that's some two motivations of doing the minimally enclosing ellipsoid. So then now I really get to go to the technical part of this talk. So the first part I want to do is I want to revisit a method by Nie and Denbo in 2005, which is they proposed a hierarchy of enclosing ellipsoids via sum of squares programming. I'm going to show you that this method has some interesting results, maybe some advantages over the confidence ellipsoid of least squares estimation by the seminal work by, I think, from Colt in 2011. And then I'm going to go into some computational enhancements that we made to make this framework maybe a little bit more practical for some applications that we care about. So the setup here is, I consider a basic semi-algebraic set, which is a set defined by polynomial inequality constraints or equality constraints. And then I consider that zeta, which is a subvector of my full parameter theta. For example, the reason I want to consider a subvector is that when I have the rotation and translation, I may want to enclose them separately, right? Because they have different units. I don't want to enclose them as a single ellipsoid. And then I denote S of zeta, which is the restriction of this set onto the subvector zeta. And then I consider a d-dimensional ellipsoid, which is written by this inequality constraint, 1 minus this quadratic form with a positive semi-infinite matrix E, which is a shape vector, a shape matrix, and the center mu. Right? So this is my representation of the ellipsoid. And then my goal is to find the minimum volume enclosing ellipsoid of this basic semi-algebraic set. So you can write down this optimization problem where I want to find the center mu and the shape matrix E such that I maximize the log det, which is equivalent to minimizing the volume. And then with this constraint that this ellipsoid should enclose this set that I'm interested in, right? So and then you can write this as a constraint saying that for any zeta in the set, it must belong to the ellipsoid, right? So that's the equivalent way of doing this. And then you can convert this constraint into a non-negativity constraint, right, which is 1 minus p theta minus mu, which is, this ellipsoid constraint must be non-negative for any theta in this set S. And then for this control crowd, we are very interested, where sum of squares is a very useful tool in this community. And anytime you see a non-negativity constraint, you know that we can relax it as sum of squares constraints, right? So I will relax this non-negativity constraint as a sum of squares constraint. I'm going to say that this 1 minus quadratic form is equal to the sum of some SOS polynomials and my defining constraints. And then here the sigma I and lambda I are SOS polynomials and arbitrary polynomials. So this is almost a convex optimization problem. And then the only, except that this 1 minus the quadratic form is not a convex. But then you can do some simple trick. I can use a lifting trick, which I reparameterize this ellipsoid as a shape matrix E and sum B, that is actually the shape matrix times the center itself. And then you can prove that this formulation is the same as the original. So now you get really a convex optimization problem that you can actually implement yourself in YAML, and then you can solve this type of problems. And then you see that there's a relaxation order, kappa here. And then you can, by Nie and Denbo, they prove that if you solve this hierarchy of convex optimization problems, I'm already 12 minutes? Okay. So you solve this hierarchy of problems, you get a hierarchy of ellipsoids, and then they will converge to the minimum enclosing ellipsoid. And then I can do this comparison with least squares ellipsoid. And you see that in many cases, you actually get smaller ellipsoids than the confidence ellipsoid. And the reason is because these actually, I think the set membership estimations are actually biased estimations, right? So you see that the set membership ellipsoid, they are not centered at the true parameter. And then by doing this bias estimation, you get certain advantages in getting a smaller volume of these set members of these ellipsoids. Okay, and then I'll just briefly, maybe 30 seconds, go through this. How can you do the computational enhancement? So really, the big problem in here is that when you solve this convex optimization problem for some large-scale problems, log det gives you the issue. Right? You use MOSAC, and you find that these problems do not converge. Although they theoretically converge, but then in practice, you get numerical issues that this convex optimization problem or this SCP is solved in an unknown status. Then I really didn't solve the convex optimization properly. And then the way to mitigate this issue is that we decouple the estimation of the shape and the center. The problem is you can formulate this min-max problem, where in the inner max, for any center mu, I'm going to find the maximum distance to the set, and I enclose it. And then on the outside, I try to find different centers that give me smaller and smaller ellipsoids. And then this problem is not very easy to solve, but then you can show that you can use the dual side of the sum of squares relaxation, which is moment relaxation, and then you can convert this into a single level convex operation problem, or SCP, and this actually generalizes the what's called the Chebyshev center that was proposed by Alda, Beck, and Tabou in many years ago. Okay, so I'm gonna end with some results on random linear system identification, and you can see that when you go higher above the hierarchy, you really get smaller and smaller ellipsoids, and then usually the second order relaxation is much better than the first order. And then here I'm going to show you that on some linear systems that are hard to learn, this method is also adaptive to the difficulty. Right? You get smaller ellipsoids if the problem is hard, and this automatic adaptation. And then lastly, there's this long horizon trajectory, and with that, I'm going to end my talk here.
Thank you. Maybe any very quick question?
Yes, I think you mean a union of ellipsoids. I think you can, but the problem will be more complicated, I feel. At least I haven't seen, when I did the literature review, we didn't see much work on that. I think you can, yeah.
Next presentation is by Rickard, who is local here at Oxford.
Hi everyone, I'm Luke. I'm presenting some work on learning robust policies for Markov uncertain parametric Markov decision processes that I completed with Alessandro Abate and Kostas Margellos here at the University of Oxford. So to start with, I'm going to introduce a small toy example, which I'll use throughout the presentation, and that's a robot planning problem. So I've got a small 3D grid, and I want to move my robot, who starts off in this bottom left corner, up to this green star in the top right corner, and there's some janitor moving around in between the states who I want to avoid crashing into. And this example is a Markov decision process, which comprises 3 key things. So in particular, I've got some states, which are the location of the robot and the location of the janitor. And I have actions, so I can try and tell my robot where to move. In this case, if he's in the bottom left, I can tell him to move right, or I can tell him to move up. Importantly, I can't control the motion of the janitor. And then I have some transitions. So once I've chosen an action, then I have some distribution over next states, which in this case arises because of the janitor. So perhaps I move to the right, and there's a 75% chance that the janitor moves up, and a 25% chance that the janitor moves down and then crashes into me, and it's game over. Now, with that in place, I can sort of take you through an overview of the talk. And in particular, I'm interested in finding how can I behave when, rather than having this MDP, I have some unknown distribution over MDPs. So I don't know exactly what my transitions look like, but I want to work out how I can perform. And I've developed some techniques that allow us to act optimally into the future in this sort of setting with this unknown MDPs, even if we don't get to actually find out the transition probabilities for an MDP in the future. And I can even provide some guarantees on how well we can behave in this setting. This extends some work by Tom Badings at the University of Nijmegen, which was looking at finding policy for every single MDP they sampled, whereas I'm looking at finding a single robust policy that will work for every MDP I sample, even if I don't get to see what the transitions look like. Now, that sort of gives you an overview, but I want to give you some definitions, and in particular, I'm looking at an uncertain parametric MDP. To start with, I'll define a parametric MDP, where rather than having some concrete transition probabilities, my probabilities depend on some parameters. So in this example, perhaps my parameters relate to my janitor. So maybe I've got this red janitor on the left here who prefers to move up, or I've got a yellow janitor who prefers to move to the right in my MDP. Then I can define an uncertain parametric MDP by putting a distribution over these parameters. So rather than having some ability to choose my parameters, these are a random variable that gets assigned to me, and I have to work out how to deal with that. So perhaps there's some distribution over which janitor turns up on any given day, but some stationary distribution. I assume not to know this distribution. I don't make any assumption on its shape. It doesn't have to be Gaussian or anything. All I need to do is have some access to some samples from this distribution. So perhaps I've seen which janitors have turned up over the past year and kept a record of what the MDPs associated to those janitors look like. To uncover a trajectory in this uncertain parametric MDP, I need to first sample a parameter, so a janitor from this distribution, and then I can play out in what is that defined MDP from that janitor by doing the standard things and looking at the states and taking an action and going to the next state. Now, dealing with this full probabilistic distribution is rather hard and potentially impossible because we're going to define an optimization problem, and dealing with this distribution would require us to have an infinite number of optimization constraints. And this is only made worse by the fact that we possibly don't know what this distribution looks like. So instead, as I mentioned, we're going to take samples and have a look at how we can deal with this sample set. And I want to find a single policy that's robust to all these samples. Now, a policy tells me how I can behave in my MDP, and in particular, I'm going to look at a few classes of policies. The simplest class is deterministic policies, where if I'm in this state here, then I always move to the right. And I can sort of say maybe that's not enough, and I want to look at some randomization, in which case I can look at a mixed policy, which says that I basically put a distribution over deterministic policies. So perhaps I choose with a 40% chance to deploy a robot that always moves to the right in this state, and if he ever returns to this state, he'll still move to the right. But maybe on a different day, there's a 60% chance of deploying a robot which moves upwards in a state. Now, with a mixed policy, if I ever return to that state, I always take the same action in a given trajectory. So instead, I can look at a behavioral policy which randomizes in a slightly different way and has a distribution of actions within any given state. So in this case, there's a 60% chance of moving to the right and a 40% chance of moving up in this state. And hence, if I return to that state, then there's a chance that I'll take a different action to what I took last time. Now, behavioral mixed policies are very similar, and for an MDP, are basically can be shown to be equivalent. But for a UP MDP, they define slightly different behavior. If you're interested in these policy classes, I'd recommend checking out the paper. I'm going to focus in on behavioral policies for the rest of this presentation. And I mentioned that I want to find a policy that works well. What I use to check if I'm working well is probabilistic computation tree logic. So I can define some labels for my states. And in particular, I'm looking at two labels. So first, I've got a label which says whether or not I've crashed, so whether my janitor and my robot are in the same state, and whether or not I've reached my goal state. And I can then specify some objectives. So perhaps I want to say with a probability greater than 1/2, I avoid crashing until I reach my goal state. Obviously, because this is a non-deterministic system, I can never guarantee with certainty that I don't crash. But perhaps a probability of 1/2 is a bit conservative, in which case I would be interested in finding what's the maximum probability of satisfying my specification. Then with this background, I can give you a formal problem overview. And in particular, I take a UPMDP and a PCTL formula, and I solve this optimization problem to find the maximum probability of satisfying that formula and find the policy that gives this maximum probability. And then I provide some probabilistic guarantees that next time we sample an MDP, we can satisfy our formula with that probability bound that I found in step 2. Now, my question is, how do I find a robust policy that works well for all of my samples? And in particular, I'm going to always look at the worst one. So for a slightly pictorial example, I use what's sort of, or a technique that's similar to subgradient ascent. And I start off by initializing my policy in the policy space, and I find that this red janitor is causing me the most trouble. So I take a gradient step in the direction away from him, and then I can see that this orange janitor is now causing me the most trouble, so I ignore the red janitor and take a gradient step away from the orange janitor. And then maybe I violate some constraints, so I project back into the feasible set, and I repeat until I get to some point where I stop moving. So perhaps here, the orange janitor and the yellow janitor both give me gradients that sort of push me into this constraint, so I terminate, and I end up with a policy that turns out to work quite well. Then I provide some guarantees, and in particular I use the scenario approach to come up with these guarantees. And I get guarantees that look a little bit like this, which is a rather hard equation to pass, so I can break it down. And what we start with is we look at a parameter within our parameter set, so one of the janitors that we can possibly find. And I want to ask the question, with that janitor, do I crash into him more often than I said I would based on my probabilistic bound that I guaranteed and using my policy that I've calculated? And I want to look at the probability that we find one of these janitors where I crash into them more often than I said I would. And I can bound that by some calculated risk, which I solve some polynomial to find. And this depends on three things. So the number of samples, the complexity, and the confidence parameter, which I'll get to in a second. But the complexity is loosely the number of samples that I would need to use to reconstruct the same solution. And because this is a sample-based approach, I can't say this happens with certainty. So I can say this happens with almost certainty by choosing some confidence parameter that I get to choose to be very small, so perhaps 10 to the minus 5. And then I can focus really just on this inner risk that I'm interested in. So I can provide some examples of how we manage to perform in this scenario, and we can see that my robot oftentimes manages to reach that goal state, but does sometimes crash. And yeah, he seems to perform quite well. So in summary, I presented a gradient-based algorithm for learning an optimal robust policy for a given specification, and I used some recent advancements in the scenario approach theory to provide guarantees that this policy can generalize to a new sampled parameter set. There's a few avenues for future work, in particular some sample discarding. So at the moment, if we uncover a janitor that's perhaps really mean and always tries to crash into the robot, then I have to just work out how to deal with that. Perhaps I want to ignore him because he doesn't turn up very often. And doing that would be some sample discarding techniques. I could also do with improving some performance. In particular, we suffer massively from the cursor dimensionality. So improving that would be quite key, especially for the sample discarding. And then we have still got some proofs that have eluded our grasp, particularly in the convergence of the subgradient algorithms. Yeah, that's everything. Are there any questions?
Questions? Have a couple of minutes. Maybe I can take a quick one. At some point you mentioned earlier about the different types of policies or solutions that you're looking for. I was curious about at a high level, what could you say about computationally the complexity of finding different
Yes.
policy solutions, if you want?
So it turns out that mixed policies are probably the hardest because you need this distribution over deterministic policies, and the space of deterministic policies is very large since it's however many actions you have for every state. And deterministic policies can be a little bit easier to compute, but you have some problems with it's quite hard to optimize for because you're looking for a discrete set, and without enumerating overall, then that becomes quite difficult. And then behavioral policies are, the easiest class to look at.
Thank you. Any other question? Yes?
Thank you for the interesting talk. Maybe this question is not 100% related, but just like out of curiosity. In recent years, it is proven that from Davide from Waterloo University that if you don't know anything, if you don't have any prior knowledge, knowing the probability distribution is impossible. This is mathematically proven. But you said if you don't know anything about the parameter, you can still get the distribution and try to have some control policy. Is it something possible, or do you use any prior knowledge which is hidden?
It would depend on prior samples. So I need to take a lot of samples of the parameters, and then I can guarantee that for a future sample from that same distribution. So I don't need to know that parameter in the future, but I need to know parameters from the past.
Thank you.
I think we can follow up with the next presentation. Thank you again. The next presentation is by Professor Kolmanovsky from University of Michigan.
Thank you very much for the kind introduction. This is a joint work with Xiao Li, who is a PhD student at the University of Michigan, co-advised by Professor Anouck, Girard, and myself, and Yutong Li, who is a former postdoc, and he's currently at Ford. And here we are looking at a problem of safe tracking where we have a neural network model and we have uncertainty. So we'd like to have a guard to guard against that uncertainty. The motivation for this work, we're using machine learning and neural networks in a variety of applications, in particular in automotive domain for engine control, but then also for autonomous driving. And so this brings the problem about safety guarantees with machine learning modules in a loop, as well as with other uncertainties, in particular sensing and actuation uncertainties. The basic setting is that we have a system that evolves to unknown dynamical equation, or unknown here simply means not yet characterized. And then a popular strategy in such a setting is that we would learn a dynamical model denoted by F tilde that allows us to predict the next state. And here we are primarily thinking about learning such a model from data and using neural networks. And then we employ F tilde as a predictive model for decision making and planning. Again, here we are primarily thinking about nonlinear model predictive control like schemes. The overall system is uncertain, and here we worry about neural network prediction error model. So our next state, xk plus 1 tilde, may not be equal to the actual state, which is xk plus 1. We might have state measurement noise or estimation noise. So yk is a noisy measurement of the actual state xk. And then we might have imperfect actuation where the control decision, UK tilde, that we command to the system may not be actually equal to the control signal UK, which is being realized. And so there are a couple of challenges as you try to analyze the impact of uncertainty in such a setting. One is that if you look at inputs to the neural network, and these are the states, xk and controls UK, these are uncertain quantities, and they depend on measured state and as well as UK tilde, which is our decision variable. So the neural network input uncertainty is decision variable dependent. And then the neural network itself, it's a nonlinear mapping, and so prediction of the next state requires uncertainty propagation through this nonlinear mapping. In the paper, we consider a robust control problem. How could we decide on a control action UK tilde such that the next state, xk plus 1, is safe for all possible uncertainties? So the overall system is subject to additive uncertainties of 3 types. One is the neural network prediction error. The other one is a state measurement noise. And then imperfect actuation or control error. And in this case, we assume that the uncertainties are set-bounded. And for computational reasons, we use hyper rectangles. That turns out fits very well into this framework. Now, the neural network itself, it's a multi-layer perceptron fully connected network with ReLU activation functions. This is something that's commonly adopted in contemporary neural network architectures and has good empirical performance. So these are the challenges that we've already discussed. And so the question is, how can we decide on a control action, UK tilde, such that the next state is safe? That is xk plus 1 belongs to the set capital XS for all possible uncertainties. And I'll mention this in the future as well, but here we allow the safe set to be non-convex, and it can be a union of hyper rectangles. So we can model obstacles and other types of constraints. Now, we can certainly pose a control problem in the form of an optimization problem, where you, first of all, it's a constraint optimization problem, so you have a number of constraints. You constrain feasible decision variables. You constrain your current state belongs to the uncertainty set X sub k, which contains the actual state given the measurement yk. And here we assume that the current state is known to be safe. The control actions. They belong to set u sub k, which is a function of u tilde sub k, your current decision. We have one step ahead, if you like, reachable set, or what we predict the next state will be through the neural network. And then if we account for the uncertainty in a state, this is a reachable state for the full actual state of our system, which we would like to be safe. And then what we'd like to be able to do is to somehow also be close to our target x sub r, so some reference state that is prescribed. And one way to do it would be to minimize the maximal distance from points in this one step ahead reachable set to a reference state x sub r. And of course, the challenge is that you can write down this optimization problem, but how to deal with it computationally, so how to transcribe it into something that could be solvable within a reasonable computation time. Turns out that there is quite a bit of related work to this problem, and that involves both interval computations, interval arithmetic, as well as semi-definite programming type methods. The work that is most useful to us has been the one in Russ Tedrick's group on using mixed integer programming. But there are differences in our problem setting, in particular that our control uncertainty set is dependent on decision variables. So we have to modify some of the developments there. But let me give you kind of an idea of what's going on, first of all, with in this previous work. So if you look at ReLU network and you look at neuron, so J's neuron of the ice layer, you have an input, which is Zij hat, and you have an output, which is Zij. And the basic idea is to encode the input-output relation between input and output in a form of linear inequalities with integer decision variables. So Zij hat become decision variables, and then you introduce extra decision variables, which are delta ij. These are binary integer variables, and they encode input-output relation. The basic idea is very simple. If delta ij is equal to 0, and you look at the system of inequalities that encodes the relation on the left of the ReLU unit, and if you set delta ij is equal to 1, that encodes the relation on the right of that unit. Okay. So that's very simple. Now, in our case, we have to modify this a bit because the values of the input and output are uncertain, and they lie in intervals whose lower and upper bounds depend on decision variables. As I mentioned, we work with hyperrectangles, so it's basically products of the intervals. So in our case, we have to somehow go from Aij hat, Bij hat, the interval for the inputs, to Aij, Bij, which is the intervals for the outputs. And it turns out that that can be done with a bit more complex encoding, where we use 3 binary integer variables, delta ij minus minus, delta ij minus plus, and delta ij plus plus. And so this is essentially the encoding, transcription to linear inequalities with integer decision variables. And so we have to consider 3 cases. One is on the left, when all of our input bounds are all on the left, on the right, and kind of in the middle. And once that's pretty simple to do. So exploiting this type of ideas, we could actually obtain the mixed integer linear programming problem formulation. Here for the norm, in the cost function, we use the 1 norm, which is natural in this type of a setting. And there is quite a few details to obtain MILP. I explained sort of the basic idea, how we deal with neural network, but there are a few other steps or tricks, and they are summarized in the paper. In interest of time, I will not go through these details, but you end up with MILP. A few properties here. The number of decision variables in MILP scales linearly with the number of neurons. The safe subset, X sub S, can be non-convex. It can be union of hyperrectangles. And then what we can show is that if we are able to solve this mixed integer linear programming problem, then our next state is going to be safe under all possible uncertainties. We would, of course, like to obtain recursive feasibility results, and this is the next step, but this is not done in the paper. We only guarantee next state safety, which is enough for the examples that we consider. So the two examples that we looked in the paper, one is the simple example and the other one is a bit more complex. The first one is omnidirectional robot, and here we have integrator-like dynamics in discrete time with control constraints. In this case, you can write down the neural network model basically by hand. And what we do is that we use reachability-guided RRT to plan a path of references. And then as we try to, once the path is developed, we try to follow this path by solving our MLP problem. And it takes about 160 milliseconds per solution. And that allows us to safely navigate the robot while avoiding the obstacles. This is a bit more detail, and the paper goes into a bit more interpretations of the results. We do have the code for this and other examples on GitHub based on the link shown. The other example is a bit more complex and perhaps more interesting, where we look at vehicle kinematic model. This is a unicycle-like model converted to discrete time. We use data to generate a neural network. It's not very complicated neural network, but more complex than the first example. It has 2 hidden layers and 8 and 4 neurons. Again, we solved the MLP problem to safely navigate the vehicle while avoiding obstacles. In this example, the interesting aspect is that we use a set theoretical localization algorithm developed in our previous work, where we have cameras on the walls, infrastructure-based sensing. Basically, we have cameras that themselves may be uncertain, and we use set membership to estimate the states of the vehicle, including position and orientation. And so this set theoretical localization algorithm can be nicely merged into this safe motion control framework. And that brings me to the last slide. So what we do in the paper, we developed an approach for robust reference tracking that leveraged learned neural network model to control the actual dynamics. We considered bounded uncertainties from neural network prediction and other system modules, and obtained mixed integer linear program by solving which we are able to ensure safety. Again, this accounts for neural network prediction errors as well as actuator disturbances, measurement noise. There's quite a few directions for future work, of course, but that's what we have in the paper. Stop here.
Sebastian, yeah. Maybe you.
Thank you for the nice talk. So I have 2 questions. One is you mentioned that the decision variable increased with respect to the neural network number of neurons, but can you comment on the complexity with respect to state and control input dimension?
This is an interesting question. I don't think we've done necessarily the analysis with respect to the state and the control input. This can be obviously done, but maybe we can.
In the 2 examples, like I guess the second example involved a more like complex dynamics.
Yeah, it's a third order. So what we've done was a third order. It's a third order model.
Was the computation time like kind of had to increase more?
The computation time, well, we were in the order of 200. I think I said 140 milliseconds or so. The problem doesn't get easier if you have more states, for sure. But I think the complexity would really come in more from complexity of obstacles in a high. For example, if you look at quadcopter type quadrotor in a 3-dimensional space, the problem would be significantly more complex.
The second question is I'm wondering about the kind of the stability of the tracking, because kind of you bound with this kind of set. So like within like your trajectory is guaranteed to stay within like some set bounds along the trajectory, but like within that set, like kind of is there any good stability property like?
Right. So basically the question is, do we ensure closed loop stability or convergence to the target? In the paper itself, we are ensuring feasibility, and typically the stability would have to be sort of a byproduct also of the original problem formulation, as for instance in conventional model predictive control, you often use terminal ingredients to guarantee stability. We don't consider that in the paper. So in the paper, we are primarily concerned about, well, and only concerned about ensuring the safety of the next state, how we can get MILP problem formulation. There's much room for further work, including recursive feasibility and stability guarantees as well.
Thank you. I think there are a lot of questions, so we'll follow up afterwards, okay?
Yeah, I'd be very happy to speak afterwards.
I noted there are a few more. All right, and the last presentation is from Sara Brancato from University of Naples.
Yes.
And afterwards, if you can keep to 13 minutes for the presentation, yes. About 2 minutes for questions, okay? Thank you.
Hi to everyone, I'm Sara Brancato, and today I will present my work on in vivo learning-based control of microbial population density in bioreactor. So I will start with a little bit of context, introducing the motivation and state-of-the-art of composition control. I will then move to what this project is about, so to propose a sim-to-real approach to solve the control of density of a cellular population in a low-cost bioreactor. I will present the experimental workflow, the results, and the future perspective. So composition controls aim to regulate the density and the composition of different cellular populations that comprise a consortium. So a consortium is made by 2 or more cellular populations that coexist in the same environment and they interact among each other. So one can leverage this interaction to fulfill a specific task. For example, in biopharma industry, you could use bacteria or yeast to produce a vaccine and antibiotic. So the biomass usually is grown in a controlled environment, such as a bioreactor. And to optimize the performance of your consortium, you can use an external controller that will maintain the desired composition of your consortium and optimize the production of the compounds of interest. And so our goal is to regulate the density of a population I to a desired reference. So if you look at this, at the literature, there are lots of examples of composition control, and they mainly use model predictive controllers or PID that are designed on an accurate model of the dynamics of the systems. And not always in biology you have this kind of accurate model due to constraints of the number of experiments that can be time-consuming or expensive. Another approach that was proposed was a deep learning controller that was that was validated with in silico experiments, so in simulation, that control 2 populations for a single reference. So there is a huge interest of using such strategy in this area because they are model-free, they can handle pretty well complexity, and they can adapt to a task to another. However, they do not usually generalize to different set points, so it's not trivial to achieve the regulations to different set points. And of course, the main bottleneck is the data availability. So the challenge in this area is to use learning-based control strategies, how to retrieve a huge amount of data. So one way is to parallelize your experiments and derive the features from the single cell, like the keynote that yesterday was proposed was doing. However, with compact bioreactor, you don't have that measurements. Usually your data derive from the whole population. So the amount of data derived from the number of experiments that you have available. And online training could be a possible way, but due to stochasticity of the process and the noise of the device, it could be cumbersome. And to date, we only have in silico results. So another way to avoid the need of a huge amount of data could be to use a sim-to-real approach. And this is the goal of this project, to assess if a sim-to-real approach could be a viable solution in this field to avoid the problem of data efficiency. And we mainly assume to have a partial knowledge of the system, so a simple dynamic to train in silico the neural network, so our controller, and then validated it in vivo experiments. So we started with a very simple case study, implementing a learning-based controller to regulate the density of a single population in a compact bioreactor, guaranteeing good robustness and performances through different set points. So our experimental platform is a KeyBio, that is a turbidostat that allows you to grow your cell in the main chamber, thanks to the temperature regulation. And you can measure the concentration of the population inside through the optical density measurement. And you can change the concentration of the population inside the vessel, administering fresh media, so diluting the volume, and removing the waste. And you implement your controller in the computer board. So the KeyBio imposes us some constraints that are the sampling time and the maximum pump rates that is set to 0.02 for safe use of the device. So here I'm showing you the pipeline of the sim-to-real approach. So first we derive a very simple mathematical model that approximates our dynamics, and we identify the parameter of the model with a single experiment. Then we train with in silico experiment our DQN agent, and we deploy the control policy with in vivo experiment. So first thing, the derivation of the model. So we characterize the growth of bacteria, E. coli, assuming that inside the bioreactor, the nutrients are abundant with respect to the biomass. This simplifies a lot the model derivation. So here's the model that we consider. X is the concentration of the population, that is the optical density measure. U is the control input to the pump rate. And so the model consists of two terms, the one of production, that it's characterized by mu-max, that is a constant growth rate, and the dilution terms characterized by the control input that is scaled by a factor tau. So here's the experiments that we consider. So in blue, we have the data that were collected with the KeyBio, and so you can see the different colors so that correspond to different phases during the experiment. So we have first phase of growth, so no dilution, a constant regulation, a regulation to a constant optical density of 0.3, and then a constant dilution to fixed pump rates. And we identified the two parameters using ordinary least square implemented in MATLAB. And as you can see, the yellow line that is the R model capture qualitatively the data. So we use this model to train a DQN agent that approximates the Q function with a neural network that consists of a first layer of two nodes, one for the measurements and the other one for the reference, two dense layer, and the output layer that consists of 17 nodes that correspond to the Q value associated to each action that were discretized on 17 level in the range of working. So the reward function is the following. So it's a negative quadratic reward function with respect to the reference. And to guarantee that our controller is able to regulate to different set points, we generate randomly the reference at the beginning of an episode in this range. And this is the cumulative reward throughout the whole training phase that consists of 100 episodes. And onto the deployment in the in vivo experiments. Here are the results of regulation to a fixed OD of 0.5 that is in red. We have 3 replicates of 30 minutes each that are shown in gray in the plot, and in blue we have the mean value. And we also performed the same experiments for the regulation of different set points, and we evaluated the performance of the controller using integral square error and the integral time-weighted absolute error. And as you can see from the table, the performances are uniform throughout the 3 regulation examples. We also compare our controller with a PI that is implemented in the KeyBio board, and a model predictive controller that was designed on the same model that I showed you before and optimized the action with a swarm particle optimization. So here I'm showing you the metrics, the integral square error and the integral time-weighted absolute error for these specific experiments, so the regulation of 0.5, and looking at the other experiments and the robustness analysis, the performances are comparable among the 3 controllers. This is also due to the fact that the device imposes a limit on the performance due to the sensing and the actuation. So in conclusion, our experiment confirmed the feasibility of using a symptom-real approach to regulate the density population in a low-cost bioreactor. We tested a DQN controller and compared its performances with a model predictive controller PI. We could think of improve our approach, adding noise or stochasticity during the training phase. However, we think of implementing it and test this strategy or a more complex scenario, because we think that the benefits would be highlighted better. And in fact, we are planning to move to composition control. We already presented an architecture that allows us to control 2 populations that compete for the same substrate, that consists of 2 bioreactors. And so if left uncontrolled, the population that grows faster will prevail over the other, leading to the extinction of this lower one. So we added a reservoir in which we grow this low population. And we implemented the strategy, the architecture, using 2 key bias, and we designed a model-based control strategy to regulate either the ratio, so the composition, and the optical density, so the density of the whole consortium. Next step is to implement and to see the benefits of using a symptom-real approach, which in this more complex scenario, we think that would be more evident. So thank you for extension, and I would wish to thank all the people behind this work, and you again for your attention.
Any questions? Yes.
Okay, thanks. Did I understand correctly, the sim-to-real, the way you do it is you train in simulation and then you use what you trained on the real system,
Yes.
right? So what I then don't understand is why is the DQN better than the MPC? Because you train the DQN on that model, so it can only be as good as the model. And if you then use the MPC with that model and you solve the MPC to optimality, then it should be better. So how can the DQN be better than the MPC? Or is the MPC not solved to optimality?
So the the model is just an abstraction, so it's not really the what's inside the bioreactor. The both controllers were tested in vivo, where the model predictive control used the simple model, but then was exploited in vivo with the real bioreactor that its dynamics, it's not exactly the one captured by the model. So they're both doing their control on the same knowledge, on the same simple model.
Yes, I understand this, but then are you saying basically the DQN got lucky because it trained something else than the model, or not perfectly for the model and just ended up being better on the real system?
No, we are not saying that it's better on the real system. We are just comparing the performance, and what we are expecting on a more complex scenario where the model, it's not key, but the structure of the control is important. Maybe it's better use a DQN approach or a learning-based control approach that you can fine-tune later on the experiment. This was just an example, a prime case study to assess the feasibility of using a sim-to-real approach in this scenario.
Oh, okay.
But we're not saying that the DQN is better on the model predictive controller because the performances are comparable.
No more questions. Okay. I think let's thank the speaker one more time. And